this course, we will go over BGP routing policies. The course covers BGP route summarization, regular expressions, AS path filter, community filter, IP-prefix list, filter policy, and route policy. Let's start with BGP route summarization. On large-scale networks, if route summarization is not performed, a large number of routes need to be stored, which adversely affects link performance. Currently, all dynamic routing protocols support route summarization. BGP supports both manual and automatic route summarization. The following points regarding BGP route summarization should be noted. First, the automatic summarization function is disabled by default. You can enable the function as required. Second, the automatic summarization function takes effect only on BGP routes imported using the import route command. Third, the routes imported using the import route command are summarized based on the major network. Summary routes are added to BGP, whereas specific routes are suppressed. The automatic BGP route summarization function has limited control over summary routes. That is, routes can be summarized only as a major network route, and refined mask control is not supported. In this example, R1 and R2 belong to AS100 and AS200, respectively. They are eBGP peers. The import route command is run on R1 to import direct routes to BGP. By default, these specific routes are sent to R2. After automatic route summarization is enabled on R1, the summary route 11.0.0.0/8, rather than the specific route 11.1.1.0/24 is sent to R2. In addition to automatic route summarization, BGP supports manual route summarization. BGP has two manual summarization solutions. In the following figure, R1, R2, R3, and R4 belong to different ASs. R1 and R2 each are connected to two network segments. R1 and R2 advertise the routes of the network segments to R3. By default, R3 and R4 learn the four specific routes. Now, it is required that route summarization be configured on R3 to simplify the routing table of R4. If we use the first solution, we need to configure a static summary route on R3 and then import the route to BGP using the network command. In this case, R3 sends the summary route to R4. In addition, we need to configure a routing policy to prevent R3 from sending the four specific routes to R4. This solution has many potential problems. For example, if the four specific routes become unavailable, R3 still sends the summary route to R4 because the four specific routes are not associated with the summary route. The second solution is to run the aggregate command for manual route summarization. You can specify parameters as required. This solution is recommended. If the aggregate command is run without any parameters specified, the summary route 172.16.0.0/16 is generated on R3, and R3 sends it as well as the specific routes to R4. In this case, the route summarization has no effect. In addition, after R3 advertises the summary route to R1 and R2, a routing loop may occur. If you specify the detail surprised parameter in the aggregate command, R3 does not send the specific routes to R4. However, the summary route has no path attributes of the specific routes. After R3 advertises the summary route to R1 and R2, a routing loop may occur. We then check the BGP routing table of R3. As shown in the command output, the summary route is marked with the asterisk and right angle bracket, indicating that the route is valid and optimal. The 4 specific routes are marked with an S, indicating that the routes are suppressed. This slide shows detailed information about the summary route. The aggregate route field indicates that the summary route is originated from R3, and that the AS path attribute is empty. This slide shows information about the update message that R3 sends to R4. The AS path attribute contains only the AS number 300, and the AS path attribute of specific routes is lost. If the AS set parameter is specified in the aggregate command, the summary route inherits the AS path, origin, and community attributes of the specific routes. As shown in the figure, the AS path attribute values of the specific routes are presented using the AS set in the summary route. The AS path attribute of the specific routes helps prevent the routing loop. This slide shows the BGP routing table of R3. We can see that the summary route inherits the AS path attribute of the specific routes. This slide shows detailed information about the summary route. As we just mentioned, if the detail suppressed parameter is specified in the aggregate command, all specific routes are suppressed. To suppress only some of the specific routes, we can specify the suppress policy parameter in the command. And of course, a suppression policy also needs to be specified in the command. If the suppression policy works in permit mode, the specific routes that match the policy are suppressed. If the suppression policy works in deny mode, the specific routes that match the policy are advertised. In summary, the suppress policy parameter configures BGP to advertise one or more specific routes. The route policy following the suppress policy parameter in the command is used for route filtering through if-match clauses, not for setting route attributes through an apply clause. The attribute policy parameter can also be specified in the aggregate command. The attribute policy parameter must be followed by a user-defined route policy. Through the apply clause of the route policy, route attributes of the summary route can be set. The last parameter is origin policy, which indicates the origin of specific routes. If only the detail suppressed parameter is specified in the aggregate command, R3 generates a summary route and advertises it as long as one specific route is available for R3. If the 4 specific routes are unavailable, the summary route is not advertised. If the origin policy parameter is specified in the aggregate command, R3 generates a summary route and advertises it as long as one specific route that matches the route policy following the origin policy parameter is available for R3. If all the specific routes that match the route policy are unavailable, the summary route is not advertised. If both detail suppressed and origin policy parameters are specified in the command, the specific routes that do not match the route policy are not suppressed. Next, let's talk about the regular expression and AS path filter. A regular expression is a formula used to match a character string according to a template and is widely used. For example, after we enter a cell phone number during registration for Internet access, the background program uses a regular expression to determine whether the phone number is valid or just a series of digits. Therefore, regular expressions can be powerful tools. In BGP policy deployment, you can also use regular expressions to filter routes. On large-scale networks, the AS path is usually complex, but you can use regular expressions to match routes whose AS path carries specific AS numbers or content. First, let's look at the composition of a regular expression. Generally, a regular expression can contain two types of characters: conventional and control characters. The control character may be an atomic, multiplication, or range character. For example, the regular expression 100 matches any character string that contains the consecutive digits 100, such as 100200, 10000, and 21412100. For more concise matching, you can add a control character. Now, let's take a look at the characters that may be used in regular expressions. This slide shows atomic characters. Period matches any single character, including spaces. Caret indicates the start of a character string. $sign indicates the end of a character string. Underline matches any delimiter, such as caret, $sign, or a space. Pipe character indicates the OR relationship. Escape character converts the subsequent control character into a conventional character. Let's look at several examples. The first regular expression matches a character string starting with A and ends with any single character. The second regular expression matches a character string that starts with 100, followed by a delimiter. The third regular expression matches only the character string 100. The fourth regular expression matches a character string that ends with 100 or 400. The last regular expression matches only the character string 65000. A multiplication character follows an atomic or conventional character and is used to describe the repetition mode of the character before the multiplication character. Asterisk matches a character string in which the character before the asterisk does not exist or the character appears multiple times. Plus sign matches a character string in which the character before the asterisk appears once or multiple times. Question mark matches a character string in which the character before the asterisk does not exist or the character appears once. Square brackets indicate a range. You can also use a hyphen to specify a range. Let's look at some regular expressions with multiplication characters. The first regular expression matches character strings that do not have C's or have multiple C's. The second regular expression matches character strings in which C appears at least once. The third regular expression matches character strings in which C does not appear or appears only once. The fourth regular expression matches character strings in which BC does not appear or appears only once. The following is an example of a range character. The first regular expression matches character strings that contain A, B, C, or D. The second regular expression matches character strings such as A, A1, 62, 1B, and XV2. The third regular expression matches character strings that do not end with A, C, or T. The fourth regular expression matches character strings such as 159, 220, and 9170. Let's focus on how to use regular expressions in BGP. BGP has an AS path filter, and the filter can be associated with a regular expression to match AS path. Each AS path can be viewed as a character string. For example, the AS path 123.495.602 is a character string separated by 2 spaces. You can run the AS path filter command to configure an AS path filter and associate it with a regular expression to match the AS path attribute of BGP routes. Then the policy is implemented on the routes that match the AS path filter. This slide shows an example. The IPS path filter 1 permit 443 command configures an AS path filter named 1, and the specified regular expression is 443. This regular expression matches any character string that contains 443. If an AS path contains multiple AS numbers, the AS numbers are separated by spaces, and the spaces can also be matched using regular expressions. Here are some examples for matching the AS path using regular expressions. The first regular expression matches the routes, those in the local AS, whose AS path does not contain any AS number. The second regular expression matches all routes. The third regular expression matches the AS path of 100. In the sixth regular expression, the second caret indicates a denial. If routes fail to match an AS path filter, the routes are denied. Let's take a look at the configurations for matching the AS path using a regular expression. First, we need to run the IP as path filter command to configure an AS path filter with one or more regular expressions. Then, run the peer as path filter command in the BGP view to apply the AS path filter to appear in the inbound or outbound direction. This slide shows 3 relevant display commands. The first command displays information about the configured AS path filter. The second command displays information about all routes matching the regular expression in the BGP routing table. The third command displays information about all routes matching the AS path filter in the BGP routing table. AS path filters have 2 application modes. We have already mentioned the first application mode. Now, let's take a look at the second application mode. First, we need to configure an AS path filter. Then, create a route policy with the AS path filter being specified in the if match clause and in which the apply clause is used to set the local preference attribute of the routes matching the AS path filter. Finally, we need to apply the route policy to a peer. In this example, the route policy is applied to the peer with the IP address of 10.134.4 in the inbound direction. In this way, the local preference of the routes received from the peer is set to 100. Let's take a look at this configuration example. A router in AS600 sends a route to R2 in AS200. R2 sends the route as well as a locally originated route to R3 in AS300. It is required that a routing policy be configured on R3 to filter out the route originated from AS600. Here is another example. This network is the same as that in the previous example. It is required that a route policy be configured on R2 to prevent the route originated from AS600 from being advertised out of AS300. In this case, we can configure a route policy to set the community attribute of the route originated from AS600 to no export. Note that we need to configure an empty node for the route policy. Otherwise, the other route that is originated from AS200 is filtered out. Now, let's talk about the community filter. As we mentioned in earlier classes, community is an optional transitive attribute. You can set a unique community value for each type of route. After a downstream device receives the routes, the device can identify the routes according to their community values and implement differentiated policies accordingly. This method is more convenient than the traditional method that is based on the route prefix. Now, let's talk about how to set a community for BGP routes. In this topology, 3 routers reside in different ASs. R1 has 2 direct routes 1.1.1.0/24 and 1.2.2.0/24, and the 2 routes are imported to BGP. It is required that a routing policy be configured so that the route 1.1.1.0/24 carries the community value of 100 to 1, and the other route does not carry a community attribute when they are sent to R2. By default, the community attribute is not advertised with the routes. To allow the community attribute to be advertised to appear, run the peer advertise community command. The command must be run on R1 and R2, and the specific peers are R2 and R3, respectively. In addition, an empty node must be configured. Otherwise, the route 1.2.2.0/24 is not transmitted to R2. In this example, route policy RP permit node 20 is the configuration of an empty node. The route 1.1.1.0/24 that R2 receives from R1 carries the community value of 100 to 1. It is required that a route policy be configured on R2 so that the no export attribute is added to the route. Note that the additive parameter must be specified in the apply community no export command. Otherwise, the no export attribute will replace the existing community attribute. A community filter can be used to match the community attribute. This slide shows 3 examples. Note the difference between the configurations of the last 2 examples. In the second example, 2 community values are specified in the IP community filter configuration in one line, and the relationship between the 2 community values is AND. In the last example, 2 community values are specified in the IP community filter configuration in 2 lines, 1 attribute value in each line, and the relationship between the 2 community values is OR. The Internet parameter can be specified in the IP community filter permit command to match all routes. In the previous examples, routes match a community configuration so long as the community value specified in the configuration is included in the community attribute. To enable strict matching, specify the whole match parameter in the ifMatch community command. In the topology, R2 receives two routes, 1.1.1.0/24 and 1.2.2.0/24, with two community values from R1. It is required that a route policy be configured on R2 so that R2 deletes 100 to 999 from the community attribute of the route 1.2.2.0/24 when advertising the two routes to R3. In this case, we can configure a community filter to match the route 1.2.2.0/24, create a route policy to reference the community filter, and configure an apply clause to delete the community value of 100 to 999. If you want to delete multiple community values, you can run the IP community filter basic permit command multiple times to match the community values to be deleted one by one. Now, let's talk about the IP-prefix list tool. This tool has a powerful range of functions and can be used to match the prefix length, and prefix length range. In BGP, the IP-prefix list tool can be used to filter routes. In this topology, R1, R2, and R3 are in different ASs and maintain eBGP peer relationships. R1 imports two direct routes, 1.1.1.0/24 and 1.2.2.0/24 to BGP and transmits them to R2. By default, R2 advertises the two routes to R3. It is required that R3 do not learn the route 1.2.2.0/24. In this case, we can configure an IP-prefix list on R2 to deny the route 1.2.2.0/24 and permit the other. Then, configure the IP-prefix list as an export policy for R3. This slide shows the key configurations of R2. The configurations allow R2 to learn only the route 1.1.1.0/24 from R1. Now, let's talk about the filter policy tool, which can also be used to filter routes in RIP. This slide shows the configuration of the filter policy that is based on an ACL. Note that the value following 1.2.2.0 is 0 instead of 0.0.0.0 in the ACL rule configuration. In the first example, route filtering is based on an ACL. In this example, an IP-prefix list is used to meet the same target. In this example, a filter policy is configured for R2 to filter out the route 2.1.1.0/24 when R2 advertises direct routes to R3. An IP-prefix list is used to deny this route and permit the other. Note that the direct parameter must be specified in the filter policy IP-prefix export command to apply the filter policy to the direct routes to be advertised. Last but not least, let's talk about the route policy tool, which is the most practical and powerful among routing policy tools. The route policy parameter can be specified in many BGP-related commands. This slide shows only some of them. The if-match clauses of route policies can be associated with many parameters, such as ACL and AC path filter. Root policies can also be used to modify many attribute values, such as the AS path and cost. In this topology, two director routes 1.1.1.0/24 and 1.2.2.0/24 are imported to BGP on R1 using the network command. It is required that the route 1.1.1.0/24 carry the community value of 100 to 1, and that the route 1.2.2.0/24 carry the community value of 100 to 2. The key configurations of R1 are shown on this slide. In this example, the requirement is the same as the previous one, but the root policy parameter is specified in the peer command. In this topology, R1 imports 3 director routes. It is required that a root policy be configured on R1 to filter out only the route 1.1.1.0/24 when R1 advertises BGP routes to R2. In this case, we can perform the configurations shown on this slide on R1. That's all for today. Thanks for listening.